All right. Just so your common knowledge, you are currently being recorded, right? Audio, not video. So, starting off for today, calendar. Here's our calendar for the rest of the week. On Friday, we went over the last type of introductory stoichiometry problem. That was a mass problem. Today, I wanted to give you one more mass problem to review, just to make sure that we got that stuff down. Then, we wanted to talk about the last stoichiometry idea, and that is percent yield. So we'll talk about percent yield today. It's pretty easy, especially if you understand math. We've talked about percentages before, so hopefully that will be clear. Okay? Then, tomorrow in class, I will devote to reviewing for tests. So if you have questions, or if you just need me to go over things like what you should be looking for on the test, or whatever, okay, tomorrow is the day. I can talk about some things, but I would rather, if you guys have questions, that'd probably be a good thing to do, bring those tomorrow, okay? Then, tests on Friday over all the chemical reaction stuff. So it is a long test. I haven't finalized it yet, but it's probably going to be around the 40-point range, something like that.
40 points?
It's about 3.5 words.
40 points? I'm so happy.
I mean, it's a lot of stuff. So, you know, it's about 3.5 weeks worth of class time. Yes, John?
Is there going to be a section like on quiz 2 where you have to this is single replacement?
Yes, absolutely. We'll figure out what you're going to do. Yes, absolutely. There will be definitely identifying types of reactions.
How many are you allowed to tell me?
I haven't finalized it yet. So all right. That's our plan. Then that will be the end of our chemistry section of physical science, and we'll be on to physics next week. So we'll introduce some new terms, talk about a couple new things there. It'll be good times. So easy. Your 40-point test that y'all excited about is coming up in 2 days. That should change.
Well, 40-point test rather than a 20-point test. Don't say that. Now watch me get like a...
All right.
Hey, your bad grade is a B. Shut up.
A grade plus isn't a bad grade.
Okay.
Yeah.
All right. Here we go. Up on the board. Up on the board is an example problem. It's a mass example problem. It is not from any of your problem sets or any of the sheets that I've given you. It's just an extra one. Okay. Why don't we start off, right? And let's work through this problem. Okay. I will give you the balanced equation. So let me do that first because the balanced equation is a little bit difficult. It was, let's see, 2 here, 8 here, and 7 there. Okay? So there's your balanced equation. The problem says how many grams of hydrogen gas should be produced from 165 grams of Si2H6 in the following reaction. Like I said, you don't have to, let's work through this together. You don't have to do it on your own. Talk to the people around you. I will slowly start putting stuff up here on the board to try and point you in the right direction. Okay? So, I will slowly start putting stuff up on the board to start pointing you in the right direction, so you can work, or so you can see whether you're going in the right way or not. While you were looking at your phone, worrying about your grade, I said. While you were looking at Missy's phone, worrying about your grade, I said this is not from any of your problem sets. It's just an example problem that I have that
Now we have to change it to molar mass first.
So, as far as the recording goes, I'm just going to pause the recording while you guys are doing this, and I'll pick it back up in a little bit. Okay, we are back recording, so let's settle in and let's go through this real quick, okay? This is a mass problem because it's asking you for how many grams of hydrogen gas, right? And then it said produced from 165 grams of Si2H6. So it gave us a mass value to work with first. It wants us to end up with a mass value. It's probably disilicon hydride, something like that, but it probably has another name than that. So, anyway, so we start off with the value we were given. But we talked about on Friday that we can't compare grams of one thing to grams of something else. We use the analogy of like the strawberries and blueberries, right? That even though you have the same pound, right? One pound of strawberries, 1 pound of blueberries doesn't mean you have the same number of strawberries and blueberries. Right, you have a pound. Right? It's the same. So the first thing we have to do is convert this original amount of Si2H6 into moles, because we know moles and moles are the same for every element, every compound, doesn't matter. So the first conversion factor that we run into, right, uses the formula mass of Si2H6 on the bottom, and then 1 mole up on the top, because if we convert something from grams to moles, it's always on a 1 mole basis. The next step, the red one, we convert moles of one thing into moles of something else. That makes the red conversion factor our what?
Mole of mole.
Oh, mole mass, sorry.
It's our mole
Ratio.
Okay. So the red one is our mole ratio. And, Christina, where did we get the numbers in our mole ratio from? The coefficients of the balanced equations. That's why it's 7 in front of H2 and 1 in front of the Si2H6. Even though we haven't written anything here, right, it's understood that it's a 1. Go ahead.
Will we have to identify the mole ratio on a test?
Yeah, not necessarily, but I might give you, not in a problem like this, but I might give you a multiple choice question and say, hey, what's the mole ratio between these two things in this balanced equation? Like I would give you a balanced equation and then say, what's the mole ratio between such and such and such?
But then how would you do it without, would you have to figure out like this is where you do it, or you just
This, you could figure out, Ellie, this is the mole ratio regardless of what amounts that I give you to start with, right? The mole ratio depends on the coefficients of the balanced equation.
so you start with the balanced equation and put
Right.
a question.
Yep.
You have to have a question though before you have like,
Well, Julia would say, do the thing. The question could be, what's the mole ratio between H2 and Si2H6? And then it doesn't matter how much we started with. I'm only asking you for this conversion factor. The only thing I'm asking you for if I ask you for the mole ratio.
you take out that and so what's the mole ratio of that?
Yeah. The mole ratio is just the red.
So for the blue and green, no
For the blue and green, right? What are we doing in the blue and green stuff, Christina?
just sending the
We're turning grams into moles in the blue stuff, right? But then in the green stuff, we're turning moles back into grams.
Just an example of how just the not the equation, but we have the equation.
Let's go through this. So then, once we do the units on the red conversion factor, the mole ratio, we'll be left with moles of hydrogen gas. But that's not what the question asked us for, right? It asked us for grams of hydrogen gas. So then, the last conversion factor, the green one, that's just using the formula mass for hydrogen gas, which is H2, on a 1 mole basis, right? And then we end up with 37.6 or something, depending on how you round it and what you didn't round and stuff like that. Good there? Yes, go.
How exactly would the whole thing like play out after you get all the information? Like I see how you put together the different
Now it's just a multiplication problem.
multiply across.
You're multiplying a bunch of fractions together, right?
You do the fractions first.
Well, no. Well, you could do the fractions first if you wanted to, or if you're multiplying fractions, you just multiply all the tops of the fractions divided by the product of all the bottoms. How you do it mathematically, I don't care.
How do you actually like find the grams of hydrogen gas?
Well,
Weight of it?
yeah, it's hard to because it's a gas, but more because when you go to take chemistry, you'll find out that certain volumes of gas equate to certain masses, so it's more easier to do it on a volume basis, like through the density, basically. So that's more of a chemistry. All right, we good here? Okay. Today, I want to talk about. Come on. Today, I want to talk about the last bit of new information for this unit in the last part of stoichiometry that we'll talk about at least this class. And that deals with these 3 terms. Okay? Oh, the problem set that I gave you today, the percent yield problem set. There's not an outline for this. We'll see. I basically just want you to write 3 definitions down. So if you write on the back of your percent yield problem set, or if you want to write them at the bottom of the percent yield problem set and do the problems on the back.
No. There's enough space to do the problem.
You probably need more space than that, but actually, let's like to that. But in talking about the concept of percent yield, we need to define these three terms. Theoretical yield, actual yield, and percent yield. Okay? So let's start. Go ahead, right now. Theoretical yield, actual yield, and percent yield. Let's start with theoretical yield. When we talk about theoretical or something being theoretical, what does that mean? Wait, go ahead. In theory, right? Connie, is that what you were going to say?
No, I was going to say that. Well, the theory is you're trying to explain why. Wait, what? Why something's happening?
Right. When we talk about something being theoretical, right? Something that's believed to be true.
Yeah, I have a question.
Okay.
Okay, so for you know we have that class about it's starting what is between two measurements.
So, Josh, what are you going to say?
Like a theory that explains why something happened in the law.
Let's not get into that. Okay. Just like regular person words. We talked about theoretical, right? What we think is going to be true, or what we think could happen, or what we think should happen. Okay? So, the theoretical yield of a reaction is going to be based on a calculation. The theoretical yield is based on a stoichiometric calculation. What do we think we should get out of this reaction based on the numbers? That problem that you just did, that example problem that we just talked about, you calculated the theoretical yield for that reaction based on the numbers on a piece of paper, the formula masses of those compounds, the mole ratio, how much of one reactant we started with. This is how much of that product we should end up with. So based on a stoichiometric calculation. Or like it says, what should it produce?
What that lab we did?
Yeah.
We have to try that shit.
Yes, but you don't know how to do it until today. So we'll talk about that at the end of the period. So. All right, good with theoretical yield?
Maybe like outside of the beliefs.
I don't like that.
Don't worry about it. That's something that's recorded. All right, next. The next term was actual yield. What do you think the actual yield is going to be for a reaction? What it actually gives you. Sadie, how are we going to figure out the actual yield of a reaction? What are we going to have to do?
Like see what it makes after it's
Somebody said it over here.
Measure.
Measure. We have to measure it, right? So, which is,
actually
yes. Okay. So, an actual yield is what did we actually get, right? How much product did we actually make during the reaction? And the only way you can figure out the actual yield is by measuring it. To do the reaction and then actually measure what you get out of it.
what's the
Say again? No. First one says, what should the reaction produce? Whereas this one says, what does the reaction produce? And those are the two big differences between theoretical versus actual. That's it.
So like we do theoretical first, sort of like an estimation, and then actual.
So, Josh, if we go, so take us to the next step, right? When we calculate the percent of something, right? Like from math class, what does the percentage represent?
How much out of 100?
Could be how much out of 100, with 100 being the whole, but in more general, right? Even if something like theoretically doesn't add up to 100, we can still figure out the percentage, right? So we take a look at percentages as parts of the whole, right? That sound familiar? Okay. So in this case, what's the whole of these two things? Which of these two represents the whole? The theoretical yield is what we ideally would end up with, right? That's the whole. But the actual yield, that would be like the part, right? Think about your test score. How do you figure out your percentage on a test? You say again?
how much you got out of how much you could have got.
How much you got out of how much you could have gotten, right? How much you got is the actual yield of your test, right? That's your score. The theoretical yield is how many questions were on the test, because theoretically you could have answered them all, right? So when we calculate the percent yield of a reaction, we just do the same thing. And so the percent yield is a calculation. And I realize this doesn't look so hot because I changed the background to something dark, but the percent yield of a reaction is we take the actual yield. That's basically what the definition of percent yield is. Right? It's a calculation. I think I actually have a word sentence, but this is what we're looking for. So the percent yield of a reaction, we take what we actually got, divided by what we theoretically could have gotten, and then multiply that by 100%, just to turn it into a percentage.
So just multiply it.
Yeah, because when you do actual over theoretical, Julia, in most cases, we don't actually get what we thought we were going to. We should get something a little bit smaller. So you should end up with a decimal here, multiplying a decimal by 100. That turns it into a percentage.
So what is the actual here? What's going to be used?
Those are things you should know beforehand. Okay. I'll go over your lab in just a second. So, well, why don't we do that now? So, Julia, because you're asking. All right. Here's your lab from last Thursday. So if you don't have it out, it might be a good idea to pull it out so you can make notes on it. Okay. I'm just going to give you some pointers. We're not actually going to do this right now. Okay? Right now, you should have 3 numbers filling in this data table. Yes? You should have 3 masses filling in this data table. On the front side, there are 4 calculations that you need to take care of. The first calculation is actually not a calculation, it's an equation, but it says write out a balanced equation for the synthesis/combustion reaction. This reaction we have done a couple times in class, and we've talked about it, and you had to write it in your lab report and everything else, right? So, what is the equation for this reaction? What are our reactants? Missy, go ahead.
2 Mg.
Well, what are our reactants in this reaction? Magnesium and oxygen comes in the form of what? Yeah, so it's actually O2. So it's Mg plus O2, right? Those are our reactants. And then what's the product of this reaction? MgO, magnesium oxide. If you look at the periodic table, where magnesium is, where oxygen is, magnesium has 2 valence electrons, oxygen has 6, 1-to-1 ratio. Okay? You need to balance that equation. Number 2 says calculate the theoretical yield of the product based on the measured amount of magnesium reactants. Number 2 is calculating the theoretical yield. How did we say we calculated a theoretical yield? Kevin? It's a mass-mass problem. It's a stoichiometry problem. It's very similar to the one that we did at the beginning of the period. It is all generally cardiac, unless I can use for some other reason, mole, but generally the theoretical yield is going to be a mass-mass problem. Okay? And that's what it... What does it say? Theoretical yield of what? So, theoretical yield of... What's the product of this reaction? Magnesium oxide, based on the measured amount of magnesium reactants, which is one of your measurements that you took.
So we'll do so our magnesium driven was 0.10. So that we do grams of that, and then we want to get grams of that.
So number 2 is a mass-mass calculation.
From what mass?
That's something we need to figure out.
From what we
Read the
and how would you get the mass?
You have it on that sheet.
Got it.
So then, number 3 says calculate the actual yield of the reaction. Kevin, we said, how do we get the actual yield of a reaction? It's a measurement.
So in this situation, suppose you...
I will leave you with this before you say it, okay? Because I want you guys to figure it out on your own, right? You're going to have to do some addition and subtraction. Maybe not both, maybe just one, okay? But I know that's incredibly difficult math stuff, addition and you'll have to do some addition and subtraction to find out number 3, the actual yield. Okay? Then for number 4, right? What did you calculate in number 2? Theoretical yield. What did you calculate in number 3? Actual yield, and I just gave you a formula to calculate the percent yield based off of the theoretical and the actual. Okay? There is one more thing I would like to talk about before we take off. Why does this happen? How come when I do my stoichiometry calculation, I don't just end up what the answer to that mass-mass problem is? Okay? There's a couple of reasons. So the first reason is that is the idea of a reversible reaction, which you'll talk way more about in AP Chem, but at least to introduce the idea. Why did we say reactions happen? What's the whole gist of a reaction happening? Okay. Kevin.
Trying to get to a lower.
Good, a lower energy state. Okay. When we write our equations to represent reactions, we have reactants on one side, we have products on the other side. What do we separate them with? No. When we're writing an equation.
Oh, sorry, I thought we were doing like this. Okay, sorry.
When we write the equation, what separates our reactants from products? An arrow. And it's a one-sided arrow. Now, if the products have a lot less energy than the reactants started with, it's going to be a one-way street, right? It's going to flow from reactants to products. If, hopefully this will not take too long, but if we recall back from this discussion, right? Does this graph look familiar?
Yeah.
Okay. If we call this energy. Okay. This is an exothermic reaction, right? It's a pretty big exothermic reaction, and I know that because my reactants start way up here, right? But my products end up way down here. But let's say I do this. Is that an exothermic reaction as well?
Yeah.
It is. Does the one on the right release as much energy as the one on the left? Are the products of this reaction much more stable than the reactants of the reaction on the right? They're really not. Okay? And if we go back to that idea of activation energy, how much activation energy does this reaction require? Kind of a lot. Here, this reaction of the one on the right, this might not be a one-way street. Okay? Even if we form some product out of this reaction, it's really not that much more stable than the reactants of that reaction. So we may have some where products form, but then they just fall back apart into the reactants that they started with, if it happens to be a synthesis reaction or something like that. Okay? Julie, go ahead.
Would a more stable element have a higher melting point because it needs more energy for it to change?
Yeah, I'll give you that.
Okay.
So this is one of the reasons why percent yield comes into play. If we have a reaction where the products really aren't that much more stable than the reactants, sometimes not all of the reactants form products. They just don't. Okay? On the other hand, if we were to take a look at the crucible from last Thursday's lab, what was in the crucible? There was oxygen, right? What else was in there? Magnesium, okay, because those are the two reactants for our reaction. Were those the only two things that were in that crucible?
No.
No. Okay. There's all that dust that we tried to clean out, but we didn't maybe get all of it out, right? Is oxygen the only gas that's in that crucible? No, right? We get the oxygen from the air, but there's nitrogen in the air and carbon dioxide in the air and water vapor in the air. So even though we're looking for the percent yield of that reaction between magnesium and oxygen, was that necessarily the only two things that were reacting inside of that crucible? Not necessarily. So sometimes that reaction that we may be trying to find the percent yield of might not be the only thing that's happening.
What do you mean when you say some reactions?
That goes back to the energy thing that we were just talking about before.
Yeah.
Right? That, Kelly, if we go here, okay, I apologize for this because my, if we go back to this, Hallie, right? The reaction on the left, this is not a reversible reaction. Once these products are formed, they're going to stay in this form because they have way less energy than the reactant started with. Okay? But in the one on the right, there's really not that much advantage of being in the product form of this reaction. Hey, hold on.
We're actually like, recording, so when you guys are all doing your thing with your book bags and stuff, it's hard to hear.
Here, this product really isn't all that much more stable than these reactants were to begin with. So sometimes we may have a situation where these products end up forming, but sometimes those products form and then they just fall back apart into the reactants because they weren't really that much more stable to begin with. And that's the idea of a reversible reaction. So we wouldn't represent that with like a one-sided arrow. It would be more like a double arrow because sometimes we have things going from left to right, but sometimes we have things going from right to left. And that happens in the real world. Okay? Go ahead.
What causes products to break up?
If they got a little bit of energy, enough energy to get back up over this reaction or over this activation energy hump, they'd go back to being reactants that time. Okay? Yes, but not really that much. All right, and so if they got a little bit of energy along the way, they could go back to that reaction. All right, one last thing. Problem sets. This problem set. We did not do any examples from this problem set. I recorded myself doing problem number 1 off of that problem set. I will post a link on the calendar, so if you want to check out a percent yield problem, that's where it'll be. There might be, that's due tomorrow, Leanne. If you want to do it for homework, good, or if you want to do it in class tomorrow, that'd be okay too. So. The lab is due tomorrow.
So,
If you have questions, what?